All right, there we go. Let's look at the first one. All right. So we have water runs into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? All right. So let's look at establishing our variables. Well, as a matter of fact, before I do that, let's draw this diagram. All right. All right. All right. All right. So your derivative is your rate. Whenever they mention the rate, or speed or something of that nature, something per something that can be attributed to your derivative. So when we go back to our problem, it says the rate that the tank fills up is 9 cubic feet per minute. So that's why they have the volume, derivative of volume with respect to time is 9 cubic feet per minute. And then we want to know how fast is the water level rising. In other words, what rate is it rising when the water is 6 feet deep? So, and that's what the question is right here. What's the rate of y with respect to t when y is 6 feet? And so the tube, not the tube, but the tank, is in shape of a cone, conical, or is it conical? Yeah, whichever way. But it's 10 feet tall with a radius of 5 feet. So we have, let's look at our variables that we have established. I guess I'm gonna put them over here. Of the surface. All right, so these are three variables: the volume, cubic feet of the water in the tank at time t. X is going to be the radius, which is in feet of the surface of the water at time t. The depth, and y will be the depth of the water in the tank at time t. So we know that y is going to be 6 because it's going to be at 6 feet. 1 second. Sorry about that. It was a little bit of an emergency. So let's look at what we have. Derivative of the volume, 9 cubic feet per minute. Then we have y is equal to 6 feet. All right. And I know we have the volume formula. Let's see, pi r squared h. And let's see, water forms a cone with the volume. So that means we could do 1/3 pi x squared y. You know, r is your radius and y is your height. So we take that and apply it to the variables that we have. 1/3 pi r squared, x squared y. So that's just our general. All right. So let's see, we can use
Squared and
say
not
again.
just x. And so why? So you wrote 1/3 pi x squared y. Why x squared and not just x?
Well, because the formula asks for r squared,
Oh,
and
right.
so yeah,
Yep, I'm
x is
caught
our
up.
radius.
Yep.
Yep. So let me see. I think we can use similar triangles here. Okay, great. So if we want to use, let me see, not triangles. Yeah, let's see that. Similar triangles. Let's say to solve x. All right, so let's see. If I look at the similar triangles, let's go back to our diagram. We have x and y, and then we have a smaller cone, and then we have a larger cone. So is x over y is the same ratio as 5/10. So we can use that. And if we solve for x, that'll be x equal to the 5/10 go to 1/2, and then we multiply both sides by y. That's where x would be. All right, so that means our volume formula now, let's go with, all right, substitute into the volume formula. Remember that was 1/3 pi x squared y, which means that would be 1/3 pi do y over 2 squared y. 1/2 y is the same thing as y over 2. So, all right. That'll be 1/3 pi times y squared over 4 y. If I were to simplify all of that, I'll just bring it down. Volume equal to 1/3. Nope, let's do it this way. Y cubed over 12 pi. Or I think a better way of writing it. Let's go pi over 12 y cubed. Yeah, that's better. All right, so before we go any further, okay with what we substituted in?
Yeah, I'm good.
All right. Sounds good. Sounds good. So now let's say find the derivative. dv dt. Yeah. So, so we'll derive this implicitly because it's with respect to t, not y. Bring a constant out front, power over 12. Take the derivative of 3 y cubed, excuse me. Take the derivative of y cubed, so you bring your 3 down. Subtract 1 from your exponent, which is 2. And that should be what's left is dy dt. All right. We can reduce this because of the 3 and the 12. Leave you a 4 down here, 1 up here. So that should be pi over 4 y squared dy dt. All right, so that's dv dt. All right, remember what we were looking for. If we scroll back up, we want to know, what was dy dt. So let's go back down. And you see we're setting ourselves up for it. So also remember, we had a rate or a number for dv dt, which is 9 cubic feet per minute. So now what we can do is use dv dt, which is 9 cubic feet per minute, and the fact that y was equal to 6. So if dv dt is equal to 9 and is equal to this quantity, that means I can set both of those equal to each other. So that'll be 9 equal to pi over 4 y squared dy dt, and also plug in 6 for y squared. So it's pi over 4, 6 squared dy dt. And what we can do now, solve for dy dt. All right, and 4 goes into 36, leaves you with 9. So that's pi, let's go to write 9 pi. All right, divide by 9 pi. 9 pi cancels on that right. Leave me with dy dt. And the left side will cancel or reduce to 1 over pi. So dy dt is equal to 1 over pi, which is approximately 1.32. And that's the answer. And what that means for us is that the water would be rising at 0.32 is cubic feet. Well, not just feet. That's right, because we're talking about water rising, the volume of the thing. So at 0.32 feet per minute. Yep. Questions on anything I've done so far?
Nope.
All right. All right. So let's look at trying another one. All right. So a hot air balloon rising straight up from a level field is tracked by a rangefinder 150 meters from liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? All right, so let me draw a little diagram as to what's going on here. Yeah, that don't look right. Good enough. All right, so here's the diagram. So we're looking at our theta, which is our angle of elevation, and our balloon. And we got then right here, a range finder. Range finder right here. So it's 150 meters from the liftoff point, and the rate is increasing is 0.14 radians per minute. So we want to know how fast, that's another rate, how fast is the balloon rising at that moment. All right. So we only have two variables in this case. We got theta, which is the angle, in radians. So make sure you're careful with that if you're using your calculator. Because if your calculator is in degrees, it will not give you the right answer. Angle in radians, the range finder makes with the ground. And then y, which is the height, right? It says in meters. All right, so our two variables, we have theta, the angle in radians, the rangefinder makes with the ground. And then we have the height in meters, the balloon is above ground. All right, so what we know is the derivative of theta with respect to t. Radians per minute. And that is when theta is pi over 4. Now we can use our trig identities or our trig functions to establish the next relationship. All right. So what we can use is SOHCAHTOA. And just giving a recap on what that means. Sine theta is equal to opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. And then tan theta is opposite over adjacent. So SOHCAHTOA. All right, so we go back to our triangle and look at what we have. We have theta right here. We know the side that's adjacent to it, which is 150, and the side that we want to know is opposite to it. And of course, right here is your hypotenuse. This angle that's opposite your 90-degree angle will always be your, I mean, the side that's opposite your 90-degree angle will always be your hypotenuse. So we're looking at opposite over adjacent, so that's going to be y over 150. So tangent of theta is going to be y over 150, which means if I solve for y is going to be equal to 150 tan theta. All right. I think I'm doing dy dt. Yeah, I thought so. So now I can do the derivative, or let me say find. Because I know what y is, or I have a representation for y. So 150 is sitting out there. Derivative of tan theta is secant squared theta. And then I should have d theta dt. You know, once again, we're taking the derivative implicitly because I'm taking the derivative of y with respect to t. Not with respect to theta. So now I can substitute in pi over 4 for theta. Because remember, our goal is to find dy dt. If you go back to our diagram, you know, dy dt was the goal. We want to know how fast is the balloon rising at that moment, at what rate. So we're almost there. So we substitute in theta for pi over 4 for theta. Also, d theta dt 0.14, and also plug in that one as well. So let me do this as far as notes is concerned. Substitute in theta equal to pi over 4 and d theta dt 0.14 radians per minute. All right, so now let's do that. So that's 150 secant squared of pi over 4, and then that'll be times 0.14. Let me rewrite this just to make sure we're clear. All right, so secant squared theta is the same thing as secant theta squared, just a notation thing. So secant squared, not secant squared, but secant of pi over 4 is the square root of 2. So that would be the square root of 2 squared times 0.14. And all of that will reduce down to 42. So let's see, square root cancels. Leaving with 150 times 2 times 0.14. 150 times 2 is 300. 0.14, and then 3 times 14 is 42. No zeros. Take care of that decimal. All right. All right. So what measurement were we in? That's radians. 150 meters. So we're in meters. All right. The balloon is rising at 42 meters per minute. All right, so that's how we'll do that one. All right, any questions? Any questions?
Nope.
All right, let's see. What time is it? We got time. Police cruiser approaching at a right angle interstate. All right, let's see if we can get one more in there, and we'll call it a day. Right angle. Oh, this probably longer than I thought. East police. All right, so let's go to the beginning and then I'll pause, make sure you got everything before we get going. A police cruiser approaching a okay, just make sure. A right angle intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is zero point 0.6 miles north of the intersection and the car is zero point 0.8 miles to the east, the police determine with radar that the distance, between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at that instant of measurement, what is the speed of the car? All right. 0.8 y is equal to zero point 0.6. Yeah. All right. I think that's good for my diagram. So up top is the police. And that's our x variables, our y, x horizontal, y vertical. And so our rate that the police is coming down to get the car, and we would look at that as being negative because he should be slowing down to try to make this turn. So he's going 60 miles per hour, but it should be decreasing. And so we want to know what is the speed of the car. So that should be positive, unless let me see. Is he coming up to? Yeah, he's not coming up to the intersection. The police is coming up to the intersection. So that's why he should be negative 60. All right. So let's establish our variables. X is time t. Y's position of police. I think they called it a cruiser at time t. And right. And then S is the distance between car and police at time t. So the relationship or the formula that we could use is a distance formula. Well, we can go ahead and step and make sure we write this out. So we know that x is equal to 0.8 miles, y is equal to 0.6 miles. Then we have what? Derivative of y. I'll just write it down here. dy dt is negative 60 miles per hour. And ds dt 20 miles per hour. So we can use our distance formula. S squared is equal to x squared plus y squared. So we can take the derivative of this, and we're doing it with respect to t, so we have to do it implicitly once again. So derivative of that would be 2s ds dt equal to 2x not ds, dx dt plus 2y dy dt. All right. Also, we can recognize this relationship for s if we take the square root of both sides. That's that. Might need that in a second. So let's solve ds dt. So we would take that and divide both sides by 2s. So divide both sides by 2s. So the 2s will cancel on the left, leaving me with ds dt. Then these 2's will cancel out, and I will pull that s to the outside, so that's 1 over s, just to be able to write it neater. So that's 1 over s x dx dt plus y dy dt. All right, now if we want to completely write that expression in terms of just x and y, ds dt would be equal to 1 over the square root of x squared plus y squared, which is what I got back here. S is equal to the square root of x squared plus y squared times x dx dt plus y dy dt. All right, so with that, now we can substitute all values, or let's say all known values. All right, so ds dt, that was 20 miles per hour. That's 1 over square root of x squared, which is 0.8, I believe, for x. Yep. So it's 0.8 squared plus 0.6 squared for y. Then we have 0.8 dx dt plus y, which is 0.6. And then dy dt is negative 60. Ran out of room there, probably could wrote that better. All right, so now we can solve for dx dt. And I'm going to shift this over just because I want it to be needed in this. But all those numbers stay the same if you've already written it. So. All right. All right, so goal now is to get dx dt by itself. So what we can do is multiply both sides by the square root of 0.8 squared, 0.6 squared. So that will give us 20. 0.8 squared. Let me go ahead and simplify what's under that radical. 0.8. Yeah. Oh yeah, that's duh. I don't know why I pulled out a calculator. So that's 0.8 dx dt. And that's minus 36. And here we have 20. That's the square root of 1. 0.8 dx minus 36. Of course, the square root of 1 is 1. That leaves me with 20. 0.8 dx dt, 36. Add 36 to both sides. So that's 56.8 dx dt. Almost finished. Divide by 0.8. And we will finally have the answer of 70. No, that was a bit much, but we got there. And so, if I'm mistaken, car was driving at 70 miles per hour. I think that's what we were looking for. Yep. All right, so the car speed was 70 miles per hour. All right. So as far as the test goes, I wouldn't put that many of them up there at the most two. Probably very similar to what we just did here, just to get the practice in. But you'll see that on the homework as well. Questions, concerns, comments on anything before we look to close.
Nothing, man.
All right, I didn't mean to burn you out, man. I didn't know three problems would do it to us like that, but
Nah, it's cool.
so with that being said, have a good weekend. Be safe. If you have any questions, don't hesitate to email me. And hopefully, your classmates will be okay. I hope everybody's all right. Um, but yeah, so man, you have a good one, and I will see you on Monday.
All right.
All right, man. Take
We'll
care.
see if anybody actually shows up then.
Hey, man, and as they say, and then there was one. So
Yeah,
that.
right.
All right, man.